In general, when we solve equations, we solve them by doing the inverse operation of the operation in the problem. For example, if we have x plus 3 equals 7, we subtract 3 from both sides. Or 4x equals 12, we divide both sides by 4. The inverse operations being addition and subtraction, or multiplication division. When working with square root problems, the inverse operation is squaring to both sides of the equation to undo the square root. In this example that I have, one square root equal to another, I can undo the squaring or the square root by squaring both sides. And because squaring and square root are inverse operations, we're left with the argument of the square root on each side. So now my equation becomes a bit simpler, becomes a linear equation. I can solve it by subtracting x from both sides, by adding 4 to both sides, and I have a possible solution to the problem. I say a possible solution because sometimes by squaring both sides of an equation we get what are called extraneous roots, numbers that don't really belong in our solution set even though we did everything correctly. If I put 7 back in this original problem for x, I have the square root of 2 times 7 minus 4, and I'm trying to see if that is equal to the square root of 7 plus 3. On the left-hand side, we have 14 minus 4, which is 10, so I have the square root of 10. On the right-hand side, we have the square root of 7 plus 3, which is also square root of 10. They are equal, which says that x equals 7 is our solution to the problem. Let's look at a different example. The square root of 6x minus 2 equals x minus 3. The language that I used in the last problem was that we can undo the square root by squaring, and we square both sides of the equation, which means on the left-hand side I'm squaring the entire square root. On the right-hand side I'm squaring the entire side. So in both cases I'm squaring the entire side of the equation. Now it's not necessary, but it's helpful if we get the square root all by itself on one side of the equation, which this problem was set up originally like that. If I square the left side, I get the argument. On the right-hand side, remember, this is the same as x minus 3 times x minus 3. And if I square that, if I multiply that out, I get x squared minus 6x plus 9. I can subtract 6x from both sides. I can add 2 to both sides. And since it's quadratic, I have everything on one side equal to 0. I can solve it by the quadratic formula or factoring. In this case, I'll solve it by factoring. Since I have two factors multiplied to get 0, then either factor could be 0. And I get possible solutions of 11 or 1. If I check my answers, if I plug 11 back in the original problem, I have the square root of 66 minus 2 is 64, or 8. On the right-hand side, if I plug 11 in, I have 11 minus 3, which is also 8. So 11 does check out. If I plug 1 in, the left-hand side, I have the square root of 6 minus 2 is 4, square root of 4 is 2. On the right-hand side, 1 minus 3 is negative 2. They are not equal, which means 1 is not a solution to the equation. Only 11 is. A third example. I have the square root minus some value equals x. I could square both sides at this point, but it's going to get complicated on the left-hand side. It'll give us more work to solve the equation. It's best if I isolate the square root on one side. I can do that by adding 1 to both sides. And then I have it in the same form that the last problem was in. I can square both sides. The left-hand side would be 4x plus 9. And the right-hand side, remember we're multiplying x plus 1 times x plus 1. x squared plus 2x plus 1. It's quadratic. I have x squared, so I want to get all the terms on the same side equal to 0. So I can subtract 4x. I can subtract 9 equal to 0. Factor. And solve each factor equal to 0. I have two possible solutions. I want to check those solutions. If I plug 4 back in the original problem, I have the square root of 16 plus 9 is the square root of 25, minus 1, that's 5 minus 1 or 4, which x is equal to 4. So this checks out. If I plug in negative 2, I get negative 8 plus 9 is 1, square root of 1, minus 1 gives me 0, but x was supposed to be negative 2. That didn't check out. Let me give you a few examples, or a few practice problems. Just pause the video, solve the problem, and come back to the video to check your answer. In this problem, we have a square root equal to a square root. We can square both sides to eliminate the square roots, or to undo the square roots. It's linear, x to the first power, so I can subtract x from both sides. I can add 2 to both sides, and I can divide by 2. 3 is a possible answer. Let me check it in the original problem. The square root of 9 minus 2 is square root of 7. On the right hand side I have the square root of 3 plus 4, which is 7. They do equal each other, and so 3 is the solution. And one more example, or one more practice problem. Pause the video, solve the equation, and come back to the video to check your answer. In this problem, I want to isolate the square root, so I can subtract 1 from both sides. I can undo the square root by squaring both sides. On the left-hand side, I have 5x plus 1. On the right-hand side, x minus 1 times x minus 1. If I square that, if I multiply that out, I get x squared minus 2x plus 1. It's quadratic, having x squared, so let's get everything on one side equal to 0. I can subtract 5x. I can subtract 1. I can factor, factoring x out of both terms, and set each factor equal to 0. I get possible solutions of 0 or 7. If I try 0 back in the original problem, I have the square root of 1 plus 1, and that's supposed to equal 0, which it doesn't. So 0 is not a solution. If I try 7, I have 35 plus 1 is 36, square root of 36, plus 1 more, and that's supposed to equal 7. 6 plus 1 does equal 7, so 7 is a solution. Remember, in these problems, it's easiest if we isolate a square root on one side of the equation, and then make sure you square the entire side of each equation, or the entire side of each side of the equation.